Hello class. Today we're going to cover section 5.3, the complex plane and DeMoivre's theorem. So the first thing I want to talk about is how to plot these points. And so the graph is actually interesting. We still have the x-axis, but the x-axis now, instead of being the x-axis, is going to be the real axis. So basically any number that's real is going to go along the x-axis area, and then the imaginary numbers will be going via the y-axis. So this number here that we're given, we're going to go ahead and graph that. And so that's the imaginary axis, that's the real axis. And so one thing that we need to know is square root of 3 is 1.73, or about 1.73, and negative I along the imaginary would be like going down 1, right? Like a negative 1 on the y-axis. So then 1.3, negative 1 would be right there. That would be where we locate that point, going over radical 3 and then going down that imaginary negative I. And that's how you plot that. That's really how simple that is. You're just going to have to do some practice with that, but it should be very straightforward. There's a definition that I need to give you guys, and so Z is a complex number, and it's in the form of x plus yi. So really, if we go back to that number that we just had, it was z was square root of 3 minus 1i. So x would have been square root of 3 and my y would have been the negative 1. That's basically what it's saying. And then to get the distance from the origin, that's important. The distance from the origin is simply going to be the magnitude of the real with the imaginary, and we call that the magnitude. Instead of distance, it's just called the magnitude. Now z is in this form. The conjugate of z is instead of being a plus between the x and y, it's going to be a minus. And so when we find the magnitude, another way to find the magnitude is this way. Would be our z times the conjugate z. That's going to yield our magnitude. Now let me show you an example of this so you guys can see it. It's really not too bad. In this example, we want to change it so that it goes into the polar form. I must have not typed that, so just so you guys know, I'm trying to put it in the polar form. And so to get it in the polar form, I'm going to plot this so you guys can find it. Real quick, before I even do that though, I want to talk about the augment. And so the augment of z would be something like, if I plotted a point, let's say I went this way, this angle here is theta, that is the augment of z. So that angle is the augment of z. Something I wanted to let you know. Okay, so in this example here that we're going to do, we can actually do some things. And so we know that r is equal to the square root of x squared plus y squared. But we know that we know that x is square root of 3. And we know that y is negative 1 from the previous example. And both of these are going to be squared, and they're going to be square rooted. So we're going to get 3 plus 1, 3 plus 1 under the square root, or square root of 4. So r is going to be 2. So that gives us our radius is 2. And then we need to remember that sine theta is equal to y over r, and cosine theta is x over r. So we're going to get sine theta is equal to a negative 1 over 2 and cosine theta is going to be equal to radical 3 over 2. And so to find the angle, we need to be able to plot these points. And so I want to plot it so you guys can see it. So if I'm going to go radical 3, -1, it's going to be something about here, right? And so the angle that we're going to end up trying to get is the angle that gets us there. And so to get that angle there, if you use your unit circle, what value would have radical 3 over 2 and a -1/2? Well, if we reference to the first quadrant, it's pi over 6. So this reference angle here would be pi over 6, right? Negative. So then 2 pi minus pi over 6 would give us that our theta should be 11 pi over 6. And so when we write this equation, the final equation is going to be z is equal to 2, that's the r, cosine of our angle, which we now know, plus I, sine of the angle that we now know. And this is our answer. And that comes from the previous chapter, or actually from right here. I should give it to you. It's right here that we get our equation for you to have in polar form. So we can see it's r cosine of the angle plus I sine of the angle. It's not too bad, but it'll take a little bit of practice. All right, let's do another example really quickly. So here we're going to plot this point. And so from that example that we just had, we know that the formula was r of cosine theta plus I sine theta is the equation for our z. And so since we know that, we can see in this example that our r is 2 and our angle theta is 30 degrees. And so what we can do actually is, if we write it as 2, what is cosine of 30? Cosine of 30 is radical 3 over 2, and plus sine of 30 degrees is 1/2, and then we need to include our I, and this is going to give us radical 3 plus I. So now that we have it in this form, we can plot this easily. Remember again, this is the real, this is the imaginary. And so if this is the origin, we're going to go radical 3 over, or 1.73, and then up 1. This is going to be our result. And this angle here, that angle is going to be a theta of 30 degrees. But that's how we plot this point, or plot this graph. It's going to be a radius of 2, and then at 30 degrees. So we're just sliding over. Okay. Now when we're talking about product and quotient, these are two formulas you're going to want to know. This is the product, and this is the quotient. And so when we have two polar formed equations, this is how we simplify them. So you're either going to have to know, well, you should memorize these or use these on the test, have these written down. This is going to be very, very useful. So let me demonstrate this for you guys so you guys can do it. And so this first one here is going to be a product. See how it's z times w. So if I have z times w, that's going to be this first one up here. And so it's basically r1, which is a 3, right, times r2, which is a 5, and then times cosine, and the angles are going to be added. So the angle is 20 degrees plus 100 degrees, and then plus I, sine of 20 degrees plus 100 degrees. That's going to be our ZW. So then ZW is going to be 15 times cosine of 120 degrees. Clean that up a little bit. Plus I sine of 120 degrees. And so that's going to give us, that's going to be our answer right there. So we have our answer right there, cleaned up for us in a way that is usable. If we wanted to go to the complex form, we could go to the complex form by finding out what cosine of 120 and sine of 120 were, but we don't need to do that. Now let's try one where it is a quotient. And so in a quotient, what it ends up being is it's the two formulas divided by each other, but we fortunately have some rules that can clean it up and make it easier for us. So we're going to get 3 over 5 times cosine of 20 degrees minus 100 degrees plus I sine of 20 degrees minus 100 degrees. And that will clean up to be 3/5 cosine of negative 80 degrees plus I sine of a negative 80 degrees, which will clean up to be cosine of 360 minus 80 is going to be 280 degrees plus I sine of 280 degrees. And there's our answer for this problem right here. So it's really not too bad. It's just understanding and using those formulas to solve our problems. Now let's delve into DeMoivre's theorem. And so DeMoivre's theorem is simply this. So if we're given some complex number formula and we raise it to a power, it's just going to be r to that power, and then that power times the angle to create a new angle. So in this example that we have here, I can rewrite that. I'm going to go, okay, z to the third then is going to be 2 to the third cosine of 3 times 20 degrees plus I sine of 3 times 20 degrees, which is going to yield 8 cosine of 60 degrees plus I sine of 60 degrees. And I can actually clean that up to put it in standard form, because that's what they're asking us to do, is put it in standard form. So I'm going to get 8 times cosine of 60 degrees is 1/2 plus I sine of 60 degrees is radical 3 over 2. And when we clean this up, we're going to get 4 plus 4 rad 3i. And that is our answer for this problem. And the reason I went there was because it asked for us to put it again in the standard ABI form. Okay, let's do another one that's a little bit different. And this one we're given in expanded form, but they now want us to put it in standard form. So what we can do is we know that 1 plus I is actually equal to the square root of 1 squared plus 1 squared, which will give us radical 2. And we also know that this is going to put us at 1, 1 for our imaginary and real graph. And this angle here is going to be pi over 4 degrees, or radians. So now that we have that, we have some information that we're going to be able to use. So then when I go 1 plus I, I'm going to be able to say that's radical 2 cosine of pi over 4 plus I sine of pi over 4. And that's going to be radical 2 over 2 times 1 over radical 2 plus I 1 over radical 2. Oh, my apologies. So then that is going to be able to, because we have that information, we can actually now expand our problem. And so we're going to go 1 plus I to the 5th and now use DeMoivre's theorem. And so DeMoivre's theorem would tell us we're going to go radical 2 to the 5th and then cosine of 5 times pi over 4 plus I sine of 5 times pi over 4. And that will clean up to be 4 radical 2 cosine of 5 pi over 4 plus I sine of 5 pi over 4, which will clean up to be 4 radical 2 negative 1 over radical 2 plus a negative 1 over radical 2 I. And then since we want to put it in standard form, we're going to distribute through, and so I'm going to get a negative 4 minus 4I. And this will be our answer, although that's funny. Yeah. There's our answer. I hope you found this beneficial. As always, all the best.